Welcome, dynamic students. In this mini lecture, we'll be going over principles for angular acceleration for rigid bodies that are moving in planar motion. So in previous lectures, we've discussed angular velocity of a rigid body. And we've looked at it in terms of the body's rotation versus some fixed reference. So we're already starting to look a little bit at the idea of relative reference frames, because when we look at a rigid body's motion and we start to look at the 2 points that define that motion, connect them to make a line, and then look at how that line rotates, it's got to rotate versus something. It's rotating versus an external reference frame. So we took the first time derivative and we developed an expression for velocity at any point on a rigid body that's moving versus a stationary or inertial reference frame, and characterized or wrote that in terms of the velocity of another point on that rigid body that we knew, and then the angular velocity of that rigid body, and then a radius vector between those 2 points, the one for which we knew the velocity and the one for which we didn't. So that was getting us up to this lecture. So now we're going to effectively spend an entire mini lecture taking a first time derivative of that very expression. So we're going to look at, okay, what if we take this rigid body that's moving in space relative to a fixed reference frame and give it some acceleration? So we looked at the 2 points needed to define rigid body motion, looked at their positions relative to an origin and a fixed reference frame, took the first time derivative, now we're going to take the second. So this will involve what's called angular acceleration. So if a rigid body, we're going to call the rigid body B. Generally speaking, if you haven't noticed so far, the moving body is typically referred to as body B, and the fixed body or the frame of reference, which will sometimes be an inertial reference frame if we're going to start applying Newton's second law, it gets called capital F, so the script F. So we've got rigid body B moving with respect to or versus or in reference frame F. Just a little note of what seems to be common convention. Okay, we can define angular acceleration as the time derivative of angular velocity. Wow, deep concept there. Take the first time derivative, and now remember, angular velocity is the change of angle defined by some line in that rigid body on B with respect to some axis in F. So the I hat, J hat, K hat axis of F. So now we're looking at the second time derivative of that angle's change of B versus F. So we're really looking at the way 2 different reference frames are moving versus each other. So we call angular velocity the Greek letter alpha, and of course it's a vector quantity, just like, we call angular acceleration alpha, Greek letter alpha. It's a vector quantity just like angular velocity, which gets that Greek letter omega, little kind of rounded W. So the angular velocity of our rigid body in our reference frame F is just the first time derivative of the angular velocity of the rigid body B in reference frame F. And so we can call that omega vector quantity dot, or the angular position theta double dot. And because that rigid body is rotating in plane, we're only talking about planar motion, all of our angular position, our angular velocity, and our angular acceleration are all going to have vector directions normal to the plane of motion. So we're saying that we're moving in the XY plane. So our rotational velocities and accelerations are all going to have angles in the K hat. So out of plane, planar normal. Now it could be positive or negative K hat, but it's definitely going to be in the K direction for motion in XY. Okay. So we can say, for just to kind of read the slides here and get the ideas in our head, if we got a rigid body B moving in a plane parallel to XY, so it can be the XY plane at Z equals 0, at Z equals 1, at wherever, but it's moving in an XY parallel plane in reference frame. So we're referencing the motion to frame F. The angular acceleration of body B with respect to reference frame F is second time derivative of its angular position reference to reference frame F pointing in the vector normal direction. Okay, so let's apply that principle to our velocity of 2 points on our moving body and see what we can do to develop an expression for the acceleration of the unknown acceleration of some point on our moving rigid body if we have another point that we know the acceleration of reference to our inertial reference frame, or our external reference frame F, we'll call it, related to things like angular velocity and angular acceleration of our rigid body with respect to reference frame F. So we're going to go back to our velocity of point Q on our rigid body is equaling the velocity of point P in our rigid body plus the angular velocity of rigid body B with respect to reference frame F pointing in the vector normal direction of the plane of motion crossed into our position vector pointing from point P that we know the velocity of towards point Q that we're looking for the velocity of. Let's take the first time derivative. So we take the first time derivative of velocity, we're going to get acceleration. So we went from velocity of Q to acceleration of Q. And we're going to take the first time derivative of the velocity of P, and we're going to get acceleration of P. Now we're going to take the first time derivative of a product. So we're going to end up getting we're going to take the time derivative of our first term, and we're going to leave it crossed with the second, and then we're going to keep the first term as is, and we're going to cross it into the first derivative of the second. So this is basically our the cross product application of derivative of uv equals v du plus u dv. Okay, so we're going to start with taking the time derivative of our first term, our angular velocity in the planar normal direction. Well, we just get angular acceleration in the planar normal direction. And so this theta double dot is alpha. This is angular acceleration of body B with respect to reference frame F. And it's crossed into our position vector of point P to point Q. Now we're going to add to that, keep our angular velocity planar normal direction the same, and cross that into the first time derivative of the position radius vector, call it, from point Q to point P. So we end up with RPQ dot, and this should have a vector symbol. This is definitely a vector. I'm going to draw a squiggly little vector just to clarify. So now we get to wrangle with this term. Well, we've seen this before when we ended up deriving this particular expression. So we're gonna take a trip down memory lane with this little section here and give ourselves a good expression for the first time derivative of the radius vector from point P to point Q. So we start by saying we can express the vector P to Q as, good heavens, we have arrows in the wrong places, as the magnitude, our length of the line from P to Q times a unit vector that denotes its direction. This is the unit vector Q, or excuse me, U, unit vector U. And this was the one that we used to define the angle theta of the body's rotational angle versus the reference frame. That was what was moving and ended up defining our rotational position, velocity, and acceleration. And we can define our U unit vector of this line connecting 2 points on our rigid body with respect to reference frame F, our U hat and, excuse me, our I hat and J hat, which are our unit vectors for our reference frame F. So now we're connecting our a line in our moving rigid body back to the coordinate axes of our reference frame. And we did this when we derived our velocity expression up here. So we're kind of reflecting back to that. So if you want to, you can flip back in your notes and refresh yourselves, but this is just kind of rephrasing it for you. So this is another way of defining our vector RPQ in terms of that reference frame F. Okay, so we take the first time derivative of that. The length stays constant. We're not stretching anything. It's a rigid body. But then we take the first time derivative of cosine theta I and sine theta j, and then we get what's basically an expression we can relate back to u. We throw out another theta hat, and then when we go ahead and take our cross product, we can just basically continue our math. We can rewrite this expression. We're not taking the cross product from the original expression. We take this expression, and we remember that we can express this whole thing as a cross product. We've used this relationship before. So these two, this one equals that. So we can rewrite the sine cosine relationship as a cross product, and we of course retain our theta dot that moves out here over in front. We'll put the dot so you can see it. So this is just using the properties of the cross product to rewrite this. But now we've got a theta dot in the k hat direction, which we'll need later. So we can recognize that what's in parentheses here, this cosine theta I hat sine theta j hat, is just, we're back to our original u hat expression, and with the length of the RPQ, we now have RPQ vector first time derivative is simply going to be theta dot in the k hat crossed into RPQ, no time derivative. So we've now got this expression that we can drop in for RPQ vector first time derivative. So we're going to put that back in this expression and then bring all the other terms down and just rewrite them. So we've got first term is just acceleration of point P, the point for which we presumably know the acceleration. Then we've got what's effectively our angular acceleration directed in the planar normal direction, crossed into our radius vector from point P to point Q. Now, and we've got our rotational velocity crossed into this, what's in parentheses, and this one term we've just determined to be what's in the parentheses. We took our little deviation and we found an expression for the first time derivative of the radius from point P to point Q. We're representing it by what's in parentheses here. So now we have that triple cross product. We've seen this before, and we can use an identity, another product of the cross product and dot product to rewrite this in terms of the difference in some dot products. If we apply this identity to theta dot k hat cross theta dot k hat cross RPQ, we end up canceling out some of the multiplicative terms, and we end up with just negative theta dot squared times RPQ, the vector RPQ. So this is the angular velocity of rigid body B with respect to reference frame F squared, and it's got a negative side in front of it. So whichever direction that radial the angular, wrong vector direction, whichever direction that angular velocity was, clockwise or counterclockwise, that would define it as positive or negative. We flip the sign after we square it, and so that'll change the direction this points. So we can drop that in, this circle term, in for everything back here. And so we can collect terms, and we're doing a lot of algebra and rearranging. So we end up with the acceleration of our point Q with respect to reference frame F outside of the rigid body, or positioned somewhere that doesn't move with a rigid body, is the acceleration of point P on the rigid body, which we presumably know, times the product of the rigid body's angular acceleration crossed into our RPQ radius vector, minus the rigid body's angular velocity squared times vector direction RPQ. So we got three terms that we can use to get the acceleration of any point on a rigid body that's moving relative to some fixed reference frame F. If we know the acceleration of another point, we know the rigid body's angular acceleration relative to that fixed reference frame, and we know the rigid body's angular velocity relative to the fixed reference frame, and we know a radius vector that connects the 2 points, the known and the unknown. So basically just using some vector algebra and properties of relative reference frames to relate rotation and translation. So I'm going to keep the pages partway between. We can say something about the orientation of these terms relative to one another given what we know about the properties of cross products and scalar multipliers. So if we're looking at points A and B, and say A is like point P, it's the one where we know what the acceleration is. And so its acceleration vector is pointing off in this direction. If we look at a dotted line between A and B, this would be like RPQ. So we know the acceleration of A, we don't know the acceleration of B, so our RPQ would be effectively RAB here. So it's going in this direction. We know that this term is oriented along the same line, but it's going the other way. So our omega squared RAB is actually pointing from B back towards A. And we know that, of course, our alpha and omega are kind of pointing. You can use a dot or a cross to show that it's pointing into or out of the screen. So if you take something that's pointing straight out of the screen and you cross it into something that's connecting A and B, you're going to end up with something that looks like this or like this that's perpendicular. So that gives you a little bit of an idea of what's perpendicular and parallel and how how each of these terms is oriented relative to the line that connects A and B. Sometimes that's important when we're looking at what's going to move what way. We're kind of developing an idea of what's parallel to the 2 points and what's normal. It's also important to remember what's going to end up canceling out if we take a dot or cross product later. And it's also important to look at back up at our expression here, AQ, it's a vector sum. So if we look at B as being like Q, it's the vector sum of this vector, our acceleration of point A, this vector, our acceleration due to the rotational velocity of body B relative to some external reference frame, but directed in the AB direction, and then our cross product term from the body's angular acceleration. So effectively, whatever acceleration B has, it's going to be this vector plus that. So I don't know, I think it's going to end up kind of maybe going somewhere like this. Do a little quick graphical addition. So this is a vector addition. Okay, 3 terms. So we got a little more than we did for the velocity expression, but we didn't end up with something too monstrous. Okay, special cases. What if A is stationary? A is fixed, like a fixed pivot. Well, its velocity, its change of position versus some external reference frame with time is going to be, let's put a point O out here. So A is fixed. So its position versus our external reference frame doesn't change with time, so it has zero velocity and it's also got zero acceleration. If that's the case, this term goes away. And we're left with the acceleration of our other point on our rigid body B simply being a function of the rotational parts of that rigid body. So basically its body's not translating, it's just rotating. But that rotation gives any given point, other than A, some actual translational velocity components versus our fixed reference frame. So that's just a quick variation and a little thought experiment about what happens if you pin one point of a rigid body down but just let it rotate versus an external reference frame. Well, we can still use these two terms to figure out the velocity and acceleration, or in this case acceleration of any point on the body, even if we have only rotational motion versus that external reference frame. Okay. So let's do a couple of quick examples here, putting our newly minted equation to use. So we're going to start with pure translation. So we have this rigid body B, and it's being suspended by these two hinged bars that are the same length. They may not look like it in the example. And they're swinging together. And so what that does is it keeps this body moving back and forth. And it can't pivot because we've got those 2 points attached. So that configuration means that we have translation. Both of these bars are rotating versus this fixed pivot, but this rigid body isn't, because these 2 points have to stay effectively along the same line versus our external reference frame X. We can say that our rigid body is translating. I'll just put a little I hat here versus our external reference frame. We'll call this F. So like the frame of the ceiling here is our external reference frame. Okay, what was wanted? What is the acceleration of body B? Okay, so basically we would know that if we could find the acceleration of any point on this body, we could use our newly minted equation to find that. So let's relate the acceleration of point A, which is on our rigid body. Let's use one of these bars. And this is actually dabbling somewhat into a relative reference frames, relative motion kind of argument. We've actually got a couple rigid bodies here. We've got body B that we're looking for an expression for acceleration of B, and because it's translating, all we need to do is find the acceleration of any one point on it. Every other point will be following in lockstep. Definition of rigid body, definition of translational motion. But what's defining the motion is actually a second rigid body, and it's this rigid connector bar from A to O. So what we really need to know is the acceleration of point A, because that's on our rigid body B, but we're going to get it due to its relationship to another point on the bar rigid body. So we're not really looking for the motion of two different points relative to one another, or two different points on rigid body B. We're really looking for the motion of two different points on rigid body. We'll call this L. So it's a bit of a trick. So, and point A is shared by body B and body L. So it is actually going to be one point where those two rigid bodies they share, will have the same position, even though it's kind of on two different ones. So we're going to actually look at the motion of this rigid body L. And we're going to look at the motion of L with reference to our fixed reference frame, which is like, the ceiling that these bars are bolted to, up where the hinges are. Okay, so our point that we know the acceleration of with respect to our fixed ceiling reference frame is O. It's the hinge. And the nice thing is its acceleration versus the ceiling is 0 because it's bolted to the ceiling. It's the hinge. We drilled some holes and bolted it down. It has no acceleration versus the ceiling. Okay, great. So we're just going to keep flipping back. So AP was 0 for that. So now we just need to look at the other two components of acceleration of that rotating bar. So first we can develop a radius vector from our point of known acceleration O to our point that we're looking for at OA. Well, that's just going to be the length of the bar, which we're told is 1 meter. And because we've got a reference frame, I hat increasing to the right and J hat increasing upwards. These are 45 degrees, so we're going to have a radius vector from O to A of negative 1 meter cosine 45 minus 1 meter sine 45, which we've got here. And this is our first term, so we've got our angular acceleration of our connector in the k-hat direction crossed into our ROA. So were we given that? They're both clockwise. We were told alpha is 3 radians per second and it's going in the clockwise direction. So a positive angular velocity or acceleration, given the way we've defined our xy coordinate system, for our fixed coordinate system, it's increasing counterclockwise. So our alpha is actually negative 3 radians per second squared. So here's our alpha expressed in our chosen coordinate system convention. Okay, so we're going to subtract our angular velocity squared, so times our OA. So what we did was we took 4 radians per second, squared it, and multiplied it by ROA, and we got this term. So 4 radians per second, it's actually negative 4 radians per second because it's going clockwise rather than counterclockwise. Negative 2 radians per second. We squared it, we got positive 4 radians per second. We multiplied it by a negative 0.707 in the I hat direction, so we got negative 2.83 meters per second squared I hat, negative 2.83 meters per second J hat. And then we got a negative sign out in front of the whole shebang, which is this one. So lots of places to make sign errors. And the biggest one is our angular velocity and acceleration expression with respect to our chosen reference frame. So when we slap down a set of coordinates, an axis system for our fixed reference frame, that's going to define what is positive and negative omega and alpha for the rigid body and bodies moving. So as soon as we put x increasing to the right and y increasing upwards, we define counterclockwise as positive for omega and alpha. So since we were told they're in actuality clockwise, we have negative values for them both. So, but okay, we're ready to go. We now have the acceleration of point A on our big suspended rigid body in terms of all numbers and no variables. So all we have to do is do one cross product and combine I terms with I terms and J terms with J terms, watching our signs. And here's some steps through the algebra, and we end up with an acceleration of point A of something in the positive I hat and J hat directions. So it's something like that. Totally different than our angular accelerations and velocities. Key points. We were asked for the acceleration of one body, but to get that we had to apply our relationship of accelerations of points on a rigid body to a completely different rigid body versus a fixed reference system, and then tag the common point. So that's something that is probably, I would call it the crux of the problem, is to recognize that we really had to use the motion of one rigid body to infer the motion of a second. But that's great. They're pinned together. So that's why we have connectors. Okay. Let's try another problem where we've got maybe some curved curvilinear things, and maybe we're going to have a rigid body that has some more rotational motion. So we've got a rod and it's moving on a parabola y equals x squared over 2. This is a problem that we looked at in a previous lecture in terms of relating velocities of B and A. So we're going to expand on that and say, okay, great. Let's see what the accelerations are. We've already solved for velocity. So we're going to pull in some data from that previous problem, and I'll just let you know that, we brought this over, we already solved it. But we are given the magnitude of the velocity of B. We're told it's constant. So its acceleration is 0. It's going to be handy, right? We're going to have, that V, that A of one point on our rigid body is 0, so we're only going to, the motion of the other is just going to be due to the alpha and omega contributions. But we need to know angular velocities and angular acceleration, which we may have to infer from something else. In fact, we will. So we have our velocity, our full velocity at B. It's 0.3 meters per second, and it's directed tangent to whatever the path is here. And we figured that out in the previous question. And we know what the direction of acceleration and the direction of velocity is of A, because it's following this path, so it's directed straight in the positive I-hat direction. And of course we can write an expression for a radius vector from B to A. Okay, so we've got all the components we need to deploy our acceleration of one point of a rigid body in terms of another, in terms of angular velocities and accelerations. And this time we've only got one rigid body and the reference frame that contains our path. So we don't have the complication of a second. So we are going to bring over our full expression for the velocity of B from our previous problem. And in our previous problem, we used that and co-developed our angular velocity of the rigid body, which we're definitely going to need for that third term in our acceleration. And we also have the velocity of point A. So again, this is a tangent normal kind of coordinate system problem because we're looking at things that are normal and tangent to the curve. So we're gonna set up our acceleration expression instead of in terms of I and J. We're going to set it up in terms of tangent and normal. So we're going to start with our tangent term. So we're going to start with point B, and we're just going to express it not necessarily related to point A. So the acceleration of point B in tangent normal coordinates, this is just thrown back to tangent normal kinematics. We're not relating anything being on a rigid body. So we've got the acceleration in the tangent direction, s double dot, so s being path length. So this is being directed to whatever direction's tangent to the curve at that point. And we were told the speed of VB is a constant. Well, that means that term's 0. Yay! Plus the velocity of point B squared. Hey, we got that. It's this thing divided by the radius of curvature at B, which we've calculated previously, and we can calculate anywhere using our mathematical expression for radius of curvature of any function at any point. And so we can get a numerical expression for the acceleration at B, which happens to all be in the normal. probably because it's moving at a constant velocity, is this term, and we know what direction it's pointing. Okay. So we can express that it's all in the normal direction relative to the parabola. We can break that up into I hat, j hat, if we need to, for reference to our coordinate system, to our x and y, because obviously the normal to the parabola and the tangent aren't the same as our I and j at that point. So if we go ahead and do that, and we transform just this single term normal to the parabola and say, okay, I want to just resolve that vector into an I hat, j hat relative to my coordinate system. Here it is. So that's in the dotted circle. So I've got two ways to express my acceleration of point B, in a tan normal coordinate system and in an ij relative to the parabolic path. So you can think of the I hat, j hat as the fixed reference frame if you want, and you can think of the tan normal as kind of maybe more the moving one. You're moving along the path. Okay, let's do the same thing for A. Let's do a tan normal action for A. So the nice thing here is that the position of A means that our normal direction is the j hat axis, and our tangential just happens to be the I hat axis. So this simplifies things. We've got those two coordinate systems are literally superimposed at that one point for this parabolic motion. So we've got whatever the tangential acceleration happens to be for point A, pointing in the tangent direction, which is also the I hat direction. And then we have its velocity at that point, which we solved in our previous problem. And so we have a numerical value for, and we have a numerical value also for our radius of curvature. So we have an expression for acceleration of point A with only one unknown. We don't know the tangential acceleration, which is also the I hat acceleration. Okay, A and B are on the same rigid body. We now have a full expression for acceleration of point B with respect to we'll call it our fixed reference frame coordinates. We have an expression for the acceleration of point A in terms of our fixed I hat, j hat coordinates, and we've only got one unknown in it. So we could start, and we know they're on the same rigid body. We have a radius vector between the two of them. So we could start populating our acceleration of 2 points on a rigid body that's rotating and moving with respect to a fixed coordinate system, and just start putting in the things we know and see if we can't come up with enough equations to solve for the things we don't. So we're gonna express our 2-point rigid body acceleration equation here with acceleration of point A relative to our fixed reference frame of the I hat, j hat coordinate system. Over here is our unknown because we've actually got one part of it we don't know. We know everything in the acceleration of B because we know both components. We don't know the angular acceleration of the rod relative to the ij coordinate system, but we do know this. So we know this and we know this. We don't know that. We've got one unknown over here. We know this from our previous work to find velocities, and we know this. Aha! So we have two unknowns. The tangential component, or I hat component, of the acceleration of point A with respect to our reference ij coordinate system, and we need the angular acceleration of the rod. Okay, because we're working in 2D, this acceleration expression, of course, effectively is two equations in one because we can separate all the I hat terms and the j hat terms. So we have two equations and two unknowns effectively. So all we have to do is input everything we don't know. So here's our acceleration of of point A in I hat j hat with our one unknown here, and here's our acceleration of B term. Here's our alpha. Already crossed into these two terms are this cross product. Already cross producted out, multiplied out, crossed out. No, that would be like not quite the same. Multiplied out. Vector multiplication. And then our scalar expression for the rod's angular velocity relative to the ij coordinate system squared, and then multiplied over our radius vector is these two terms. So collect terms, solve. Collecting terms will allow us to write an equation that relates the tangential part of our acceleration at point A and our rod angular acceleration, and then we drop down to our j hat term to solve directly for the angular acceleration, substitute, and we get both answers. So key points here. Recognizing first of all what we had and what we didn't have. And it's interesting that if we were given, this is a note, if we know something about velocity and we know something about relative position, it's useful to go ahead and solve for everything we know, especially about angular velocity of a rigid body with respect to our reference coordinate system, because we know that's going to be one term in our acceleration that we'll need. So go ahead and do the work with velocity first, then see what we need to do for acceleration. We always have our expression relating acceleration at 2 points on a rigid body to each other via the angular velocity and acceleration of the rigid body with respect to a fixed reference system. But there's nothing wrong with pulling out our basic kinematics and using that to maybe solve for some unknowns or to shed insight that we need to create some expressions that will tell us what we need to know. This still holds. We just need to make sure that we're not mixing coordinate systems in our final expression. Our normal tangent system is great for point B, but we did have to go transform it to our reference coordinate system to plug it down into here. So basic rigid body movement gave us the answer we needed with a little help referencing a tan normal coordinate system expression. And that was it. Okay, next topic up will be application of all of these 2 points on a rigid body that is rotating and translating with reference to a fixed coordinate system, a fixed reference frame. We're going to apply it to describe rolling in our next few lectures. So stay tuned for that.